So thank you very much for the introduction, for being here with me today after yesterday's presentation. So this is the last slide from yesterday. And what I did yesterday was to discuss with you some properties of a remarkable semigroup that explains a lot of properties of geometric objects on a Poisson space. This is the Ornstein-Uhlenbeck semigroup. I was describing to you the eigenspaces of this semigroup that are the so-called Wiener chaoses, that are spaces of multiple Wiener integrals of a fixed order Q. And so these are objects that are defined as you define stochastic integrals in calculus by L2 approximations and isometric formulae, and should be really thought as equivalents of Charlier polynomials for the one-dimensional Poisson distribution. And indeed, if you isolate in your Poisson measure one single Poisson random variable, and you take a function of this single Poisson random variable and you expand it in multiple integrals, then it turns out that your multiple integrals are the Charlier polynomials. So it's really a genuine generalization of this. And my last proposition was that these objects, these multiple integrals, enjoy a number of properties that are important for us. One is that exactly the eigenfunctions of the Ornstein-Uhlenbeck semigroup with exponential eigenvalues. They verify an isometric property and orthogonality property. They decompose each random variable, and they react, and they have a very nice behavior with respect to the add one cost and add minus cost operators that act on them by just removing one order of integration, multiplying by the order of integration, and letting one variable free inside the integral. Okay, so I can rephrase, I can restate these properties in a cleanest way. Sorry? Is there a question? No, maybe just only voices. Okay, good. So I can rephrase what I just say to you in a more explicit way. If you take a function f, which is square integrable and measurable with respect to the sigma field generated by the Poisson measure, then this function can be expanded in an infinite sum of multiple integrals of increasing order. Then this sum is orthogonal and is converging in L2. And then by previous remark, the action of the Ornstein-Uhlenbeck semigroup, of which yesterday I gave a description in terms of conditional expectations and thinning, can be also seen in or characterized in a spectral way by saying that given a random variable of this type, the Ornstein-Uhlenbeck semigroup acts by multiplying each Wiener chaos projection by the exponential of minus Q of t, where Q is the order of the chaos. And of course, by the orthogonality property, one also has that the variance of the function f is just the norm of the kernels of the chaos decomposition squared, multiplied by this combinatorial factor Q factorial. So one remark that I would like to make now that it's going to be useful for our discussion later, which is a trivial remark, is that now if I divide this series here, if I divide each of these weights that are here by the variance of f, then what one obtains is a probability measure on the integers, of course. And the properties of this probability measure on the integers are relevant for our discussion about the Poincaré inequality. I would also like to point out to you a formula, which is due to last Penrose, that tells you that on a Poisson setting, the kernels of this chaos decomposition can be characterized always in a quite clear geometric way. They correspond to 1 over Q factorial, the expectation of the Qth iteration of the add one cost operator that I described yesterday. So the operation of putting one additional mass to your configuration and then subtracting the original value of your function. So let me just tell you that this is a formula that is equivalent to a formula on the Gaussian space, which is known as the Schulte formula on the Gaussian space. But on the Gaussian space, on the Gaussian space, instead of having discrete operators like the add one cost operator, one has gradients or Malevin derivatives in an infinite dimensional setting. So in this Schulte formula holds under very restrictive assumption on the regularity of the function f here. It should belong to an intersection of an infinite class of subpolar spaces, which is not the case on the Poisson space. This formula is completely general and can be applied to any situation. Okay, now I have the spectral description of the Ornstein-Uhlenbeck semigroup, and it's quite easy to describe the generator, which corresponds to taking the derivative at 0 of this semigroup, and by asking that the convergence of the derivative takes place in the L2 norm. And so due to this form here, it is quite easy to prove by direct computation that f belongs to the domain of the generator of this ortho-Uhlenbeck semigroup, if and only if the norms of the projection of the function on the corresponding Wiener chaoses converges when this is multiplied by the amplifying factor q squared. And in this case, the action of L over f is just the sum of minus q. So it's minus q, the order of integration, which corresponds to taking a derivative of this guy here at 0. And what one also has, something that can be proved by using our characterization of the add one cost and add minus cost operator that we're pointing out later, is that this quantity here, which is therefore given by the series of the multiple Wiener integrals multiplied by minus the order, has also a trajectorial, an omega by omega representation as the integral with respect to the intensity measure of the add one cost minus the integral with respect to the original Poisson measure of the, what I called yesterday, the remove one cost. And you can really prove this by hand by plugging this expression of the add one cost and remove one costs that I gave here into this expression. And then by observing that if you apply this expression to a single multiple integral, then you have exactly minus the order of the integral IQ. And so these are all properties that are useful and can be used. So both representation of L of f in a spectral form or in a omega by omega form are useful for geometric applications. And okay, so this is the this is just a representation of different quantities that are related to this Orstein-Uhlenbeck semigroup. And of course, once one has the generator L, one can define the pseudo inverse L minus 1 of f, which is defined for every square integer random variable by simply multiplying each chaos projection by minus 1 over q, not particularly original as a definition. And then the crucial formula that we are using in many occasions, we will use in many occasions during my discussion, is that one can develop starting from here and from this representation of the different objects, an integration, what we call an integration by parts formula. And so the name integration by parts formula is because it is in particular a perfect counterpart to the integration by parts formula on a Gaussian space. And it tells you the following. So if you have a random variable which is in the domain of the generator of an Orstein-Uhlenbeck semigroup, and you have another random variable such that the add one cost operator is a square integrable with respect to this product measure, then the expectation of LF times G is equal to minus the expectation of the inner product of D plus F and D plus G with respect to the intensity measure. So I could prove this in at least two ways. I can just use the chaos decomposition of LF, the chaos decomposition of G, compute the covariance by orthogonality, and then compare with the quantity that is here by using the representation of D plus F and D plus G that is related to this representation of the add one cost operator. But another way, which is even more interesting, is that one can use the omega by omega representation of the generator of the Orstein-Uhlenbeck semigroup, which I recalled in the little square here, so which is the integral of D plus minus the integral of D minus. You can plug this representation of L into the expectation that is here, and then apply, as I said yesterday, the Mecke formula. So it's this L1 formula that allows one to pass from integrals with respect to the intensity measure to integrals with respect to the eta measure. And so as I was anticipating yesterday, actually, so this crucial formula, which is this integration by parts formula, is explained by the Mecke formula, which is the fundamental identity on the Poisson space. Okay, so this is a bit of formalism, which is a completely standard formalism in the semigroup theory. The truly important formula that I'm going to use in the next slides are this chaos decomposition and this representation of the variance as a series, converging series of norms of kernels of the chaos decomposition. Okay, so now one last piece of information is the following. So now that we know, I'm sorry, that the action of the add one cost operator of a multiple integral has this form, so removing one order of integration and multiplying by the order, we can clarify some statements that I made yesterday. So in particular, one can use, once again, the orthogonality and isometric properties of multiple integrals to prove that the add one cost operator of a random variable is square integrable with respect to the product measure of probability and the intensity measure, if and only if the series of the norms of the projection of inner chaoses multiplied by the amplifying factor Q is converging. So which is something less than the requirement that the random variable. Other questions? Just one.
Question.
So that this series is converging once the factors are multiplied by Q squared. In particular, so this norm that is here, it's equal to the series of the variances of the projection of inner chaoses multiplied by the factor Q. Okay, so this is a series of relations that can be deduced from the definitions and the orthogonality properties. Now I come to the centerpiece of the first part of my presentation, and this is the Poincaré inequality on the Poisson space. So this is something that I wanted to look at and to use as a sort of guideline for my presentation. So this is the Poincaré inequality. I cannot really, I mean, I should have done this research. I think it comes from end of the 80s, probably in the beginning of the 90s, Christian Audrey-Privot, but probably it was known before. So I won't just give you bibliographic references about this. And so the Poincaré inequality that I'm stating in a slightly stronger form that the usual form in which is presented is the following. So now assume that you have a random variable f, which is a square integrable. And now the variance of f can be bounded in two stages. So the first stage, you take 1/2, then the expectation of the add one cost operator squared, integrated with respect to the control measure of the Poisson process, and then plus 1/2 the expectation of the square of the add one cost operator. So in this expectation, the square is inside, and here the square is outside the expectation. And once again, everything everything integrated with respect to the control measure lambda. And of course, by Jensen inequality, this is bounded by the usual right-hand side of the Poincaré inequality on the Poisson space, which is just the expectation of the integral of the square of the add one cost operator. Okay, so it's a slight strengthening of the Poincaré inequality, but I used actually this strengthening at least at one point in my life, so I like to state it. And so this is an equivalent of the Poincaré inequality on a Gaussian space, which is we know that if you have a smooth function of a Gaussian vector, then the variance of f of g is less or equal to the expectation of the gradient of fg to the power 2. Okay, so it's an equivalent of that where the role of the gradient is replaced by the role of the add one cost operator. And the proof, so there are several proofs available. The proof that I sketch in my notes here is a proof which is based on the chaos decomposition of the spectral decomposition of the variable. And so it goes as follows. So you know the variance of f, you can decompose it as follows. So you take the norm of the projection on the first chaos squared, plus the sum for q going from 2 to infinity of q factorial, and then once again the norm of the qth kernel in the chaos decomposition. So this is the variance by my previous computation. Now let me recall also to you that this u1, due to this formula by Last and Penrose, is the expectation of the d plus operator at x. So it is exactly the quantity that is squared inside the first line, the first right-hand side of my chain of inequalities. So it is exactly given by this formula by Last and Penrose. Now what I can do is the following. I can multiply, I can write 1 as 1/2 plus 1/2 here. And also I can make the observation that since each q here is bigger than 2, in this sum, then q over 2 is bigger than 1, which is not particularly particularly deep remark, but it's quite useful. But because now what I can do, so once again I can write 1 2 plus 1/2 plus 1/2. So I can take 1/2 here, and then I can just bound this sum by the sum obtained by multiplying each sum by q over 2. And I can regroup this with the missing 1/2 that I took from the decomposition that I wrote here. And so what I obtain is it 1/2, the quantity which is exactly equal to the expectation of the integral of the square of the add one cost operator, and then plus 1/2 the norm of the expectation of the add one cost square, so with the square outside. And once again, this sum here is exactly equal by my previous computation to the norm of the integral of the add one cost operator, expectation of the integral of the square of the add one cost operator, and the other term is unchanged, but it gives me exactly the first line of my right hand side. As I was telling you yesterday, this inequality, the second yesterday, I was telling you 2 minutes ago, the second inequality is just an application of Jensen. Okay, so this is the Poincaré inequality on the Poisson space, which is plays a role which is analogous for the application that I have in mind, the Poincaré inequality on the Gaussian space. So it controls the fluctuation of the variable f in terms of the magnitude of the add one cost operator, which is a discrete gradient on the Poisson space. And now what I want to discuss in this, to conclude this first part, are some limits, some limitations of this inequality, and how one can overcome these inequalities, these limitations, overcoming at the same time some specific structural properties of the Poisson space, and in particular the Ornstein-Uhlenbeck semigroup, which is not hypercontractive, as I was briefly discussing yesterday. Okay, so this is the Poincaré inequality on the Poisson space.
Did you explain the set A in the statement of theorems or in the integration domain?
At the integration domain, I'm sorry, I'm just working with a Poisson measure eta on a space A calligraphic. It is just a general space. Yeah. It's just a reference underlying space from yesterday. I'm sorry, I should have recalled the.
No, thank you.
And lambda is a measure which I take to be a locally bounded measure on that.
Yeah, that's clear.
Okay. Thank you. Okay, so now in the second part of the one about actually limit theorems, not just variance estimates, I will give a direct applications I will describe direct application of the Poincaré inequality as it is in the form that I just stated, which is therefore quite useful for a number of applications. And if you want to look at the reference that I like very much, where the Poincaré inequality is applied in order to estimate variances and fluctuations in general for Poisson for a Voronoi approximation of sets in Euclidean space, you can look at this very nice paper by Heveling and Reisner, where actually the Poincaré inequality is obtained as a limit of discrete Poincaré inequalities on product spaces, like Efronstein inequality, which is a quite very instructive procedure. But I want rather to discuss some limitations of this Poincaré inequality. So my first remark is that this Poincaré inequality is, of course, it is strict. It is a strict inequality which is inequality if and only if the random variable consists of only one projection on the first Wiener case. So this I should have said. But in general, one can find quite a number of easy counterexamples or situations in which this inequality is largely suboptimal. So for instance, you can take the following simple counterexample. You can take the case of the Euclidean space, Rd, and you can take as a measure, as an intensity measure, a factor n multiplying a probability pi that I assume to have a density in order to be consistent with my underlying notation of intensity measures not having atoms. And then I can consider extremely simple random variable, which is just the indicator that the points that belong to my Poisson point configuration are such that at least one of them is outside the ball of radius t. Okay, so in particular, the red points here are my Poisson point configuration, and in my case here, this indicator is equal to 1 because there is 1 point outside t. So this is a simple random variable. We can compute everything because the event that there are 0 points in this, the number of points outside the ball of radius t is just by definition of a Poisson measure, a single one-dimensional Poisson random variable with parameter the measure lambda of the complement of the ball with radius t. And so we can compute everything about Poisson random variables. Here we're just asking that this Poisson random variable is non-zero. Okay, so I can compute everything directly. And the variance is, of course, the variance of a Bernoulli random variable, which is given by the exponential of minus n pi b0 tc, and then minus 1 minus n pi b the complement of the ball with radius t. And it's, however, easy to see what happens with the Poincaré inequality. Now, if you look at the add one cost operator, then the only way in which the add one cost operator can be non-zero is that before adding a point, so I'm adding a point z. So the only situation is the one in which all the points are inside the ball for my Poisson configuration, and I'm adding a point outside the ball. Everything else just gives you 0. And now, if you take this characterization of the add one cost operator, you can just plug this in the Poincaré inequality, and the right-hand side of the Poincaré inequality is something on the order n multiplying this exponential by times the measure pi of the complement of the ball. And if you let n go to infinity, you have this additional factor n that makes the right-hand side much bigger than the left-hand side of the Poincaré inequality. Okay, so this is an elementary example, which is some sort of this sort of example where everything is explained. It's a problem that comes with its own solution, if you want. But there is something which is more substantial, and it is the following. So remember yesterday, I was telling you that random variables that have motivated studies in the direction of improving our understanding of variances are random variables that are related to percolation events. So in particular, what I was putting forward yesterday was the indicator of a percolation event that is associated with the Boolean model, which is the event that one can travel from the origin to the boundary of the ball with radius n by just crossing the region which is occupied by the Boolean model. Okay, and in particular, what is interesting is the probability. So is the expectation of this random variable here, which is the probability of this percolation event. Now, in this case, remember that in this case, we had that our intensity measure was given by the product of a multiple of the Lebesgue measure times a probability measure on the class of compact sets. So in this case, we have a formula, which is quite well-known formula in percolation theory and in stochastic analysis in general, which is this Margulis-Russo formula, that gives us the possibility of interpreting the right-hand side of the Poincaré inequality in terms of a derivative. So what you can do now, you can take this percolation event here, and you can take a derivative with respect to the parameter that multiplies the intensity, right, which is this gamma parameter. And this formula tells us that this is actually equal to the expectation of the add one cost operator integrated with respect to our intensity measure without the factor gamma. And since the random variable I'm looking at is a 0,1 valued random variable, then this add one cost operator takes values in 0,1. And actually the random variable that is here is increasing, because if you add 1 point, then it's more probable to be able to cross because there will be more regions occupied by the Boolean model if you add 1 grain of the Boolean model. So if you add 1 grain here, then it will be more likely that the percolation event happens. And so this add one cost operator is therefore either 0 or 1, and it is therefore equal to the square. And so up to the factor gamma, this quantity here is the right-hand side of the Poincaré inequality. So why is one interested in taking derivatives of this type? It is because in percolation studies, one is interested in detecting phase transitions. So the phase transitions are therefore phenomena that are observed by letting the parameter gamma, which is the intensity of the Poisson measure, go from 0 to infinity. So the larger the gamma, the more are, let's say, the density of the grain that are deposited by the Boolean model in your model. And so the more likely are the percolation events. So what one expects is that there is a phase transition in which percolation events have zero probability, that then increases quite quickly to 1. And one way of that has emerged in several years to detect this kind of percolation events, of phase transitions, is some sort of a bootstrapping procedure that consists in relating the derivative of this theta and gamma quantity to the quantity itself. And indeed, if one interprets the right-hand side of this chain of equalities, this Margulis-Russo formula, as the right-hand side of the Poincaré inequality, one can actually do that because we know how to compute the variance of a 0-1 random variable. And what one obtains is that, I just reading this in terms of the Poincaré inequality, is that theta gamma multiplied by 1 minus theta gamma divided by the parameter gamma is less or equal to the right-hand side of the Poincaré inequality divided by gamma, which is, by my previous computation, the derivative in gamma of the probability theta n. Now, what happens is that this inequality is not enough in order to detect phase transitions. For reasons that I don't have the time to explain, one typically needs to have an additional factor here, which has typically the form that I write here like Sn over n, where Sn is the integral of the probabilities from 0 to n, and n is just the radius of the ball, right? And in order to have this correction, this corresponds to a non-trivial correction to the Poincaré inequality. And this is a more serious and more like substantial reason why one should be concerned about the optimality or not of the efficiency or not of the Poincaré inequality. So these two examples that I'm discussing are both related to the following phenomenon. So you have a sequence of random variables that are square integrable, to which one applies the Poincaré inequality, and in both situations, it is this situation and this situation before, I mean, the one that is related to this phenomenon here, one observes that actually the right-hand side of the Poincaré inequality is much bigger than the left-hand side. Basically, that the left-hand side is a little o of the right-hand side of the Poincaré inequality. So this kind of phenomenon, this kind of really of different regimes of different asymptotic behavior of the left and right-hand side of the Poincaré inequality has a name in the literature that has emerged recently, in particular by a book by Schulte, which is known as super concentration. So we say that a sequence of random variables that are square integrables is super concentrated if the variance, or the sequence alpha n of the variances, is a little o of the sequence beta n, which is given by the right-hand side of the Poincaré inequality. Okay, and so which I described as like alpha n and beta n. So we can actually, since we can represent the right-hand side of the Poincaré inequality, so we'll come to this later. But what I want to tell you is that you can encode this kind of phenomenon in terms of linear chaoses, as I will do later. Okay, so this phenomenon of the superconcentration phenomenon that I described by two examples. So as a description which is natural in terms of linear chaoses, and it is also related to another phenomenon that I would like to briefly describe, which is known as the noise sensitivity phenomenon. So the noise sensitivity of phenomenon was described, once again, motivated by percolation results by Benjamini, Kalai, and Schramm in 1999. And one says, in this Poisson setting, one says that the sequence of random variables is noise sensitive if, okay, you can take the variance to be bounded, uniformly bounded. And then if for every t bigger than 0, the covariance between the random variable fn and the random variable fn, even slightly moved by the Orstein-Uhlenbeck semigroup in the direction t, converges to and a difference between this covariance and then the expectation of fn square, so which corresponds to the covariance between fn and tt of fn, converges to 0 as n goes to infinity, right? So if you remember now, in the Meller form, this Orstein-Uhlenbeck semigroup is the conditional expectation, which is given by this thinning of the original Poisson measure plus the addition of an independent Poisson measure with the rate 1 minus exponential minus t. Since this is an expectation of with respect that involves a product with something which is sigma eta measurable, you can remove the conditional expectation here and reinterpret this quantity as the covariance between Fn and then Fn, which has been perturbed by the thinning operation and then by the reinjecting operation. And you have this noise sensitivity if this covariance converges to 0 as n goes to infinity. Now, actually, since we know how this guy acts on Fn via its chaos decomposition, we can express this covariance in this form. This is just the sum for q bigger than 1 of the exponential of minus qt, q factorial, and then the norm of the qth chaotic projection of it. And in this sense, we can say, so once this operation has been done, we can see exactly that there is a tight connection between this super concentration phenomenon and the noise sensitivity phenomenon, which can be really seen in the following string of equalities. So for noise sensitivity, we are looking at the covariance between f and the TT of f, where TT of f is the action of the Orstein-Uhlenbeck semigroup in T. By the formula that I've wrote here, this can be written as the exponential of minus qt and then this q factorial uq squared. Now, this guy is, since this is less than 1, this is lesser or equal than this sum, where the exponential has been removed, which is exactly equal to the variance. And by the Poincaré inequality, this guy is lesser or equal than the expectation of the square of the add one cost operator integrated. And by the orthonormality properties of multiple integrals, this is just the same sum that is here multiplied by q. Okay. Now, assume that the variance of f is far from 0, far from infinity, let's say of the order 1, something like this. So it's something which is the variables have been renormalized. I was telling you before, if you divide this kernels therefore by the variance, then you obtain a probability measure on the integers. And so, and what this, what the noise sensitivity and super concentration tell you is that a random variable is noise sensitive if the Laplace transform of this distribution of the integers converges to 0 for every positive t, and the moment, so the expectation, converges to infinity for as n goes to infinity. And what does it mean? This means that if one considers the spectral decomposition of your variables, so in both cases, noise sensitivity and super concentration, so both phenomena describe the fact that the mass of this probability distribution of the integers, which is formally given by the norms of the projection of linear chaoses, is concentrated on the high frequencies, right? And so the operation of taking the multiplying, so amplifying the high frequencies, like we do when we take the right-hand side of the Poincaré inequality, make this expression explode with respect to the variance of the original random variable. Okay, and okay, so this is really a phenomenon that concerns the fact that random variables of certain type have a spectral decomposition or a chaos decomposition where the mass is concentrated on high frequencies of high orders of the chaos projection. Okay, and so whenever you have this phenomenon, the Poincaré inequality is largely suboptimal. And as I was anticipating, this has been has given some sort of motivation for developing and refining and finding alternatives to this to the Poincaré inequality. So, what are the alternatives and what is available on the Poisson case? So let me first discuss what happens on the cube, on the discrete cube. So minus 1, 1 to the power n. Let me consider a random variable epsilon 1, epsilon n. So here I wrote that are uniformly distributed. So the IID Rademacher random variables with probability 1/2. You can take any parameter, and even the cube is not particular. It's not it's not important. It's not fundamental to work on the cube. You can go to other spaces. And in this case, instead, I mean, the equivalent of the Poincaré inequality is the Ephronstein inequality. And so, or discrete Poincaré inequality. So the discrete Poincaré inequality tells you that if you have a square integrable random variable of your sequence epsilon 1, epsilon n, then the variance of this is less or equal than some constant, probably 1/4 is not the correct constant, of the sum of the expectation of this delta I f epsilon to the power 2. What is this delta I is really something which is in the same spirit of the add one cost operator. It is a random variable which is obtained by taking f of epsilon and then I swapping the sign of the ith coordinate. Okay, so this is the Efronstein inequality. So you can prove the Efronstein inequality exactly as I proved at the Poincaré inequality in the following sense. When you work on a discrete cube, then the equivalent of chaos, probably I should say the equivalent of what happens on the cube is the chaos, the linear chaos. In any case, the equivalent of chaos is the Fourier-Walsh development, Fourier-Walsh expansion of functions on the discrete cube. And this Fourier-Walsh expansion gives you an orthogonal decomposition, and then you can represent the variance and this quantity in terms of this orthogonal decomposition exactly in the same way as it happens for the Poincaré inequality. That is, on the right-hand side, the high frequencies of the decomposition of your function f epsilon are multiplied by an amplifying factor. And this inequality fails to be optimal for the same reason for which the Poincaré inequality on the Poisson space fails to be optimal. And in the literature, there have been a number of beautiful results that have managed to improve or find alternatives to what happens here. So one alternative was, it's a remarkable result by Talleyrand, which is the L12 inequality from '94, which was meant to, once again, was motivated by percolation, but also allowed one to obtain a more general version of a result about Boolean function that was proved by Kahn, Kalle, and Lineal. And this is estimated by Talleyrand tells you that the variance of f epsilon is less or equal than a constant, and the same term that appears in the Efronstein inequality here, but corrected by 1 plus the logarithm of the L2 norm divided by the L1 norm. So this is a strict improvement of the Efronstein inequality. This is particularly effective whenever this guy here has the form more or less of an indicator. And one point which is important for us is that, as explained in a paper, for instance, by Cordero, Rascon, and Ledoux of 2011, so this result works. I mean, the proof of this result and all generalization for some Gaussian space of results are based on hypercontracted properties of the underlying discrete Ornstein-Uhlenbeck semigroup, something which we cannot hope to generalize on the Poisson space. And there is another remarkable result I would like to briefly discuss, which is a result by O'Donnell, Sachs, Schramm, and Servadio, which is really something a bit different. I mean, actually remarkably different. And it tells you the following. So consider again a random variable f, which is defined on the discrete cube, and it's square integrable or integrable. In this case, you just need integrable. And then assume something about the decision tree complexity of this function. So I'm not going to define everything, but one has to assume that the function f, the value of the function f, is determined by some decision tree alpha. So what is a decision tree? I'm not going to define it formally, but it can be defined in terms of iterated mapping, but it is a procedure that starts from a deterministic point and then reveals one by one the bits that are the argument of the function f and stops whenever the value of the function f is completely determined. So for instance, in my example here, the input is a string of 1 and minus 1 of length 7. And you would like to compute the function f epsilon, which is the indicator that there are more ones than minus ones. Then the value of this function can be decided by using the following elementary algorithm that tells you start from to reveal the first bit, you go to the second one, and you continue counting bit by bit, or revealing things bit by bit until you find 4 ones, which is or 4 minus ones, which is exactly this point. When you arrive at this point here, as an algorithm or decision tree, you don't need to reveal the remaining two coordinates. This can be just discarded, and so these are not revealed by the algorithm. And so each algorithm of this type brings with it a probability which is called the revealment probability, which is the probability that the bit I is revealed by the algorithm A alpha. Okay, so every point and every coordinate in the input has a certain probability of being revealed by given decision tree that determines the function f. So in this very nice and actually extremely truly beautiful result, which is known as the OSSS inequality, tells you that not exactly the variance, but something which is close, which is the expectation of the difference between f epsilon and f epsilon prime, which is an independent copy, is less or equal than the sum of the coordinates, the probability of revealment, and then the L1 norm of what already appears in the Efronstein inequality. And if a function has values in -1, 1 or 1, 1, then you can express this in terms of variance, and you can just really look at this as a true, genuine extension of the Efronstein inequality. So this inequality has had a huge impact in percolation theory, and it had also been applied to the Poisson situation, like the one that I am describing, via discretization procedure. And so, the thing with which I would like to finish my presentation here is to describe to you similar results, or the limitations, similar results on the Poisson space. Okay. So the question is that are there intrinsic forms of this L1, L2 inequality by Talleyrand and the OSSS inequality on the Poisson space? And I was telling already, there is one problem, which is the fact that the Ornstein-Luneburg-Semmelgruppe is not hypercontractive on the Poisson space. So the hypercontractivity is false. It is proved allegedly in a paper by 1984 by Surgailis. And also one has to understand what is a decision tree in a continuum setting, like for the Poisson point configuration. So I will finish therefore with the answers to these two questions. So the first thing is that as far as the L1, L2 inequalities is concerned, then things are not very exciting. In the following sense, since you do not have hypercontractivity on the Poisson space, then what one has to do is to limit oneself to a very restricted group of collection of random variables that are random variables that are negative. And no, I'm sorry, that are decreasing. So the decreasing random variable that is such that if you add 1 point, then the value of the random variable decreases. And if you don't do that, then hypercontractivity fails by very elementary counterexamples. Now, if you live with this, I mean, you face this situation, so you cannot have in general hypercontractivity, but however, you try to reproduce the original proof by Talleyrand of the L1, L2 inequality, then you end up with a restrictive form of the L1 to L2 inequality, which is quite difficult to use. That is, a similar form of the L1, L2 inequality, where this switching operator appearing in Talleyrand inequality is replaced by the add one cost operator, and the sum is replaced by an integral with respect to the intensity, only holds if the random variable is non-decreasing. So adding 1 point increases so the add one cost operator is positive, and on the other hand, the iteration of the add one cost is negative. So it is increasing and concave. So, and of course, decreasing and convex, because it's variances, you can multiply by minus. But this is basically the only cases in which we can prove this. And if you go outside that, then the inequality fails. This inequality is L1, L2 inequality fails. And in particular, the random value of my previous counterexample, the one where I proved to you that the Poincaré inequality is suboptimal, fits exactly this framework of the L1, L2 inequality. So it gives at least one elementary example in which this L1, L2 inequality beats the Poincaré inequality because it can actually be applied to something. But however, so what we have now developed in the last few months is a version of the Poisson space of the other guy, which is the OSSS inequality, one which is based on stopping sets. And so I will finish with this. Based on algorithm. So it turns out that the right notion that replaces that of a decision tree on the Poisson space is the notion of a stopping set. So a stopping set is a random subset of my ambient space A, such that the following happens. So this random set, which is a function of the underlying Poisson point configuration, only depends on the restriction of the Poisson point configuration to the set itself. And whatever other configuration I put outside the set this this doesn't affect the shape of my random set. So for instance, if I can use briefly the possibilities of my iPad, then for instance, this is my Poisson point configuration, and I can take as a stopping set the smallest ball that contains, say, 8 points. So I'm sorry, it should work better than this. 8 points, so I can do something like this, and then make the ball grow until I encounter 8 points, which should be right here. Maybe these are, okay, these are 8, so I stop here. So, and this is a stopping set because whatever I do here, whatever I add outside this set doesn't change the shape. So there are more interesting stopping sets that are, for instance, one that I do not have the time to define, which is the fundamental region of the Poisson-Voronoi tessellation, which is called the Voronoi flower. And what replaces a decision tree from the discrete setting is the notion of an attainable stopping set. That is, a stopping set that can be continuously, in some sense, achieved starting from a set with measure 0 by an increasing and continuous, in some sense, family of other stopping sets. Okay, so this is what replaces the idea that you have an underlying decision tree that reveals bit by bit the arguments of a given function, and then our results that I would like to conclude this part with is that if you have a random variable f on the Poisson space, which is determined by stopping set, so meaning that the value of the random variable only depends on the Poisson configuration inside the stopping set, then the fluctuation of the random variable, that is expressed here as the expectation of the difference in absolute value between f of eta and f of eta prime, where eta prime is an independent copy, is a form which is very similar to the Poincaré inequality, with a square missing because this is an L1 inequality, but where each point in the domain of the Poisson measure is discounted by probability, which is exactly the probability that the point lives in the stopping set, that is in the random set, which is revealed by our what we call continuous time decision tree. And this is exact continuous version of that. And so in the work that I'm quoting here, we are applying this to several models of percolation, like confetti percolation, K percolation. And as it happens in a discrete world, this kind of estimates are particularly well adapted to detect sharp phase transitions, as I was described before, and in particular to detect sharp phase transitions in any dimension. So this applies very well to the content of the school. So this is a kind of results that allow one to prove phase transitions, sharp phase transitions in any dimension. So for any value of d, under of course a certain assumptions. So I think I have to stop, right? And so I probably take a couple of minutes more. And so my last talk tomorrow will be about actual second order results, that is central limit theorems, proved by the Poincaré inequality without any correction, just the pure Poincaré inequality. Thank you very much.